Well, good morning, good afternoon, or good evening, I guess, whenever you happen to be watching this. Um, Welcome to the lessons that we're going to be doing for Math 146. Um, I want to basically start off by saying that everything that we do in this course is basically under the assumption that you have successfully navigated through Math 145 and are prepared for basically what will be the final step before you move on to calculus. As such, I will be teaching this with the predication that you have a bunch of prior knowledge that's already required to do this. So I will be using a lot of terminology and again, assuming that you already have some of the basic knowledge as we go through. So let's go ahead and get started. Our first unit is going to be, excuse me, all about advanced algebra topics. So unit one is going to be advanced algebra topics. And our first section, we'll call section 1.1, will basically be solving linear, radical, and rational equations. This should mostly be review. So we're going to be talking about linear, rational, and radical equations. So again, this entire section 1.1 here should pretty much be review. One way or the other, it's still a good thing to do is to review some of this stuff. Linear, probably be one of the easier ones. Linear just basically means obviously a line. All of your equations are going to be equations of one independent and one dependent variable, typically a y and an x, but not always. Um, and those should be relatively easy for us to solve. Rational equations are going to be a rational function itself is defined to be a polynomial divided by another polynomial. And a polynomial is any equation, excuse me, any expression where all of the variables are only raised to whole number exponents. Whole numbers meaning 0, 1, 2, 3, 4, etc. There are no decimal exponents, no fractional exponents, no negative exponents. And then radical equations are equations that simply have some kind of a radical or what more people would probably call some kind of a root function, whether it's a square root, cube root, fourth root, whatever, there will be some kind of a root. All right, so let's go ahead and get started with some examples. Try and make these as quick and easy as we can, but I'd like to run through at least a few different kinds of things so that we have an idea what's going on. So our first example, we are going to be given the equation 3 times quantity x minus 2 is equal to 5 times the quantity x minus 1. Okay, a relatively straightforward linear equation. Once again, we can tell it's linear. All the variables are only raised to the first power. So, um, probably be a good idea to distribute. 3x minus 6 is going to equal 5x minus 5. Now we've got variables on both sides of the equation, so let's get them all to one side or the other. Does not matter which. So we'll subtract 3x on both sides, leaving negative 6 equals 2x minus 5. We'll add 5 to both sides, which is going to give us negative 1 equals 2x. And then dividing both sides by 2, we get x equals negative 1/2. Considering we started off with a linear equation, assuming we did not make any mistakes, that would be the solution. In order to check that that is the solution, you simply plug x equals negative 1/2 back in to both sides of that equation and make sure you get a true statement. I am not going to bother with the check in this case. It does work. There are going to be equations that we absolutely must check our answers for. But again, since this started off as a linear equation, assuming we didn't make mistakes, we don't actually have to check. So let's go ahead and move on to a second example. And obviously, as we go through these things, if you don't feel like you need to see all the examples, these are just there for you, for your to be able to utilize if necessary. If you don't need them, skip through to whatever it is that you feel like you need to see. All right, our second example will be 2x minus 1 in quantity, x minus 1 is equal to x minus 5 times 2x minus 5. Now, some of you may have already recognized that when we go ahead and distribute all this out, it's going to create quadratics on both sides of the equal sign, and that is true, even though this is the linear section. However, you will see what happens shortly. So when we go ahead and distribute, I may call this foiling. Not necessarily the terminology everybody uses now, but since it's a binomial times a binomial, you can use the acronym FOIL. Otherwise, we are basically just distributing everything through. Again, I have to assume you understand how to do that process. You will get 2x squared. Multiplying the outsides and the insides together, you get negative 2x and negative x, which combine to be negative 3x, and then plus 1. On the right-hand side, we'll get 2x squared. Multiplying the outsides and insides together, you get negative 5x and negative 10x, which adds to negative 15x, and then plus 25. That's supposed to be a 5. There we go. Now, what you should see in order to start solving this equation for x is once you subtract 2x from both sides of the equal sign, they're going to go away, which does leave a linear style function. So the 2x squareds are going to subtract out on both sides, leaving negative 3x plus 1 equals negative 15x plus 25. Let's add 15x to both sides, which will yield 12x plus 1 equals 25. Sorry, this pen likes to drag. I'm really not trying to do that with these 5s especially. We'll subtract 1 from both sides. So 12x equals 24. Dividing both sides by 12, you get that x equals 2. And once again, this started off as a polynomial on the left, polynomial on the right-hand side. We did not change the dynamic of this function into some other type of function. It started off as a polynomial, ended as a polynomial. So as soon as you see that, you don't have to check. Again, assuming we made all the correct mathematical steps. And in this case, we did. The x equals 2 is the actual answer. Should you need to check, plug 2 back in for every x, and there you go. All right, moving on. Example number 3. Let's move on because I think that was okay for linear. I think we're probably all right with that. Let's move on to a rational equation. Again, a polynomial divided by a polynomial. So our example is going to be 3 over x minus 2 equals 1 over x minus 1 plus 7 over the quantity of x minus 1, x minus 2. Now, there are multiple ways you could go about doing this problem. You could, and hopefully you understand that in order to actually combine the stuff on the right side, you would need to have a common denominator. The common denominator here would be x minus 1, x minus 2. You could combine the entire right side, combine your numerators and go with it that way. Or you could realize that probably the easiest way to do this is going to be to get rid of all the fractions at once. Most of the time, people don't like dealing with fractions when it comes to equations just because they're a little bit more challenging. Not that they're impossible, just they're more challenging. So my method, and I think this is probably going to be a preferred way to do this, is to get rid of the fractions. Well, in order to get rid of fractions, the easiest thing to do is to multiply all of the fractions by what the common denominator would be. And your common denominator in this case, once again, is x minus 1 times x minus 2. So we are going to take this entire equation, we are going to multiply it by x minus 1, x minus 2. Now remember, when you multiply through fractions, you're only multiplying the numerator here because you're multiplying every piece on the left and the right side. So this is perfectly fine to do. So what you have to think of, probably the easiest way to simplify, is if I multiply x minus 1, x minus 2 on the top of the first fraction, the one with the 3 on the left-hand side, you'll have an x minus 2 over an x minus 2, which will cancel out, which will leave 3 times x minus 1. Again, I have to assume that you understand this process at this point. So now if we multiply x minus 1, x minus 2 times the 1 over x minus 1 part of the fractions, the x minus 1s are going to go away, which leaves just x minus 2. And then if we multiply these things by the last fraction, x minus 1 and x minus 2 both cancel out, which leaves you with just plus 7. And we have gotten rid of all the fractions at one time. Very convenient way to get this problem rolling. All right, let's go ahead and combine all of our like terms, distribute things. We can kind of do all that at the same time. So on the left, we get 3x minus 3. On the right, we'll combine our constants and get x plus 5. Subtracting x on both sides, 2x minus 3 equals 5. Add the 3 to both sides. We get 2x equals 8, and divide both sides by 2, we get that x equals 4. And once again, assuming that we did everything correct, that should be the answer. Now, this is one of those circumstances that while you may not have to check to make sure that the answers work, because we should have done everything correctly mathematically, because of the fact that we started off with rational functions with variables in the denominator, we do have to double check that our answer does not create some kind of a 0 in the denominator, because we can't divide by 0. So that would be some kind of an undefined value. So look at your denominators and make sure that x equals 4 does not create 0 in the denominator. And plugging a 4 in for x minus 2 or x minus 1 does not create 0, so we're good. That one is perfectly fine. All right, let's go to example 4. Let's do another rational function. This time we'll have x's in the numerator and the denominator. The process, however, really doesn't change. And in this particular case, the common denominator is, there's only one denominator, it's x minus 1. It's the same thing in all of them. Technically, 2 is not written as a fraction. However, you should know that you could write that as 2 over 1, which still indicates that your common denominator is x minus 1. So let's go ahead and multiply through every term, left and right, by x minus 1. Well, doing so eliminates the x minus 1 in the first fraction and leaves us with 3x. Multiplying the 2 times x minus 1 leaves you with just 2 times x minus 1. And then multiplying the 1 on the right just leaves you with 3. All right, so let's go ahead and solve. Distribute everything out on the left here. 3x plus 2x minus 2 equals 3. So I'll have 5x minus 2 equals 3. Adding 2 to both sides, 5x equals 5. Dividing both sides by 5, we get that x equals 1. Perfectly fine, well and good looking solution, with the exception that if you take 1 and you plug it back into your original, your denominator is 0. That is a big problem. So we cannot use x equals 1 as a solution. And since I had no other solutions from this particular equation, and I am pretty sure that the math was correct, there are actually no solutions to this particular problem. And when you write something that is no solution, it is indicated by this symbol. Okay, that is not a 0. Okay, for those of you guys who write your zeros with a little line through it, mathematically, that actually indicates no solution to the problem. Just letting you know. So try not to write your zeros that way. most people will understand in context if you're writing, 300 and you write 2 zeros or something that look like that. But if all you're trying to say is that the answer is 0 as opposed to no solution, don't write just the 0 with the slash to it. That means no solution. And I probably should have indicated this before. We should be writing our solutions in what are called set notation. And set notation, for those of you guys who have seen this before, should be written in what's called the braces, which looks something like this. Those are the braces. Some people call them squiggly brackets because they don't really know how to draw them very well. And trust me, it's okay. I get it. Do your best. But that's how we should be writing the solutions. While I'm not going to go fix all the ones that we did up in the prior part, the one right above would have been the solution set of 4. So that's really how those answers should be written, in a set notation. Not to be confused with a bracket, not to be confused with a parentheses, set notation. All right. Let's move on to radicals. There are other parts that we could do from this particular section, but I think we'll save that for 1.2. So let's move on to radicals. And once again, a radical just means you have some kind of a root in the equation. So in our particular radical equation here, we're going to have a cube root of 2x minus 4 minus 2 equals 0. Okay, so obviously one of the things that we should know is to undo a cube root, you would need to cube it. And since the variable is underneath of that root, we're going to have to get rid of the radical symbol in order to solve for x. The basic concept is that you want to isolate, to the best of your ability, the root. So we want to get the root all by itself on one side of the equation. So in order to do that, in this case, obviously we would add 2 to both sides. And we would be left with the cube root of 2x minus 4 equals 2. And now the root is isolated on the left-hand side. So in order to go ahead and start solving this, we are going to cube both sides of the equation. Raise both sides of the equation to the third power. So on the left-hand side, you'll get the cube root of 2x minus 4 cubed, which just leaves you with 2x minus 4. And then cubing 2 is just 8. By doing so, we have now created a linear equation. So we'll add 4 to both sides and divide by 2, which will leave x equals 6. Now, we did start off with a root or a radical equation. It is necessary in most cases to go back and substitute your value and to check to make sure everything works. More specifically, it's going to be an issue when you have even-powered roots than odd-powered roots. The odd-powered root, again, assuming we did all the math correctly, should work out. But it's a good practice when you're going from a radical equation and then simplifying it to a linear equation to solve it, to go back and check it, no matter which kind of a root it is, just in case. If you were to plug in 6, you would have 2 times 6, which is 12, minus 4 is 8. The cube root of 8 is 2, and then 2 minus 2 is 0. So this does work out. Again, I'm not writing all of that down, but you should be able to go back and check that. So your solution to this is the solution set of 6. All right, let's try another radical equation. That's number 6. There we go. All right, so we will have the square root of x minus 1 equals x minus 7. All right, move that up there. So the root is isolated, so we can go ahead and get rid of it. In this case, it's a square root, so we will square both sides of the equation. Remember that when you square the right side, you are squaring the entire right side of the equation, not each piece individually. It's the entire right side. All right, squaring the left side just leaves us with x minus 1. Squaring the right side, basically it's x minus 7 times x minus 7. Again, no matter what method you use, you're going to have to expand all that out. There are shortcuts, and hopefully you already know how to do some of these. That'll end up being x squared minus 14x plus 49. And then we will have to subtract x on both sides, because basically we have created a linear and a quadratic. So basically the whole thing becomes a quadratic, which means we got to get one side equal to 0. So let's subtract x and add 1 at the same time. If we subtract x, we get negative 15x. If we add 1, we get plus 50. All right, multiple ways to solve this equation. Probably the easiest way to solve it is to factor. Now, again, I have to assume that you understand basic factoring of a quadratic, especially when there's a coefficient of 1 in front of x squared. I personally use a reverse FOIL method. It's kind of a mental thing. You have to be able to add, subtract, multiply, and divide basically in your head a little bit. But the first term has to be x and x. There are a bunch of factors of 50, 1 and 50, 2 and 25, 5 and 10. So you have to come up with the combination of those things that's going to add up to a negative 15. Well, I do know that 5 and 10 will add up to 15 as long as both of them are negative, and multiplying two negatives gives you a positive 50 at the end. So we've gone ahead and factored this, which indicates that our solutions are x equals 5 and x equals 10. Now, once again, we started off with an equation that was a radical equation. You have to check these answers to make sure everything works. In this case, I'll actually write it out a little bit better for the check here. If I plug 5 into the original equation, get 5 minus 1 under the square root, that'll equal 5 minus 7 on the right-hand side. So 5 minus 1 under the square root is 4, which gives you 2. And on the right side, we get negative 2. Okay, that's a problem. That's an issue. That does not work. So because that is not a true statement, x equals 5 does not work. If you plug in 10, get 10 minus 1 under the root, 10 minus 7 on the right-hand side. 10 minus 1 is 9, so the square root of 9 is 3. And on the right-hand side, we also get 3. That one checks out. So your only solution to this is 10. X equals 5 is what is called an extraneous solution. Okay, again, I don't know if that was something in the previous previous courses, but this is what is called an extraneous solution. It looks like it should be a solution after what we solved algebraically, but it actually doesn't work when you return it to the original problems. And again, that is because we took something that was a radical equation and we changed it into a quadratic equation through the process of doing some algebraic work. So it looked like it should be a solution. It was a solution to the quadratic, but it does not work for the radical, an extraneous solution. All right, I think we'll do one more. Be a slightly longer problem to finish off this video, but I think it is kind of important to do. All right, so our seventh example is going to be a square root of 2x plus 3 minus square root of x plus 2 is equal to 2. All right, so what you can see here is that we have multiple radicals. The problem with trying to, and you would say, well, they're isolated, both of them are on the same side, and that is true, but the problem with trying to square both sides is you have to remember that you're going to ultimately end up foiling or distributing 2x plus 3 minus, square root of 2x plus 3 minus square root of x plus 2 times that entire thing itself. you'll actually still end up with a square root if you try and square it as it is. So the concept is, let's isolate one of them. Let's get one of them out of here. So I think it'll be easier in this case to add add the square root of x plus 2 to both sides. Let's do that. Now, at the very least, when we square both sides, we'll be able to get rid of the one on the left. So let's do that. Let's square both sides. Now we're going to have 2x plus 3 equals. We are unfortunately going to still be left over with a square root on the right, but we'll deal with that. Let me move this up a little bit. So if you were to FOIL this out, you're going to get 4. Multiplying those two terms together and then doubling the result is going to give me 4 of those square roots. And then squaring that square root at the end will give you x plus 2. And let's combine what like terms that we can. So we have, let's see, 2x plus 3 stays that way on the left. I've got a 4 and a 2 here and here that I can combine. That'll be 6. Can't really do much with the x. And I've got 4 square root of x plus 2. So I've combined what like terms I can. Now I still have that square root that I have to get rid of because it's got an x underneath of it. So now what we can do is we can move everything that's not that square root to the other side. So let's subtract 6 and we'll subtract x on both sides of the equation. Subtracting x will leave us x. Subtracting 6 will leave us with a minus 3. And what I have left over is 4 times the square root of x plus 2. So I've technically isolated the square root. I mean, I could definitely divide both sides by 4 if we want to completely isolate it. But since the 4 is being multiplied by the square root, it won't really affect anything when we square it. We do have to remember the 4 is there. We have to deal with it, but we can go ahead and do this. So let's go ahead and now square both sides of the equation. So on the left-hand side, we're going to once again have to FOIL that or distribute it, whatever, square it. It should be x squared. Multiply those two terms together, minus 3x, and double it should be minus 6x. And then square the last one, plus 9. Now, when we square the right-hand side, because I've got factors there, 4 and that square root, have to square both pieces. Remember, this works with factors. It doesn't work with sums or subtractions. So let's see, we're going to have 16, that's squaring the 4, and then times the square root of x squared plus 2 squared, which is x plus 2. And it took a while, but we've now finally gotten rid of all the radicals. So let's distribute. (16x plus 32). Write that again. Better. And we are now left with a quadratic, so we can get all the pieces to one side, set it equal to 0. So x squared, let's see, we have to subtract 16x on both sides, which will leave minus 22x. Subtracting 32 on both sides is going to leave us with minus 23 equals 0. And then once again, we can factor. So I know I'm going to have an x and an x. The only way I'm going to get to 22 in the middle is to have a 1 and a 23. Since 23 is prime anyway, the 23 will have to be negative and the 1 will have to be positive. So that gives me values of x equals -1 and x equals 23. So those are the solutions to our algebraic equation there. We have to double check because we started off originally with radical equations. So let's see what happens here. Square root of, if I plug in a -1, that will give me 2 times -1, which is -2 plus 3. And then over here, plugging in a -1 will give you -1 plus 2 equals 2. And so here we get negative 2 plus 3 is 1, so that's 1, minus negative 1 plus 2 is also 1, which is 1, equals 2. Well, that gives me 0 equals 2. That's not a true statement. Negative 1 does not work. So let's try 23. Numbers will be a little bigger here, but we can manage. Multiplying 2 times 23 is 46, plus 3, minus 23 plus 2 under the root equals 2. So 46 plus 3 is 49. Square root of 49 is 7. 23 plus 2 is 25. Square root of 25 is 5. 7 minus 5 does give us 2. That works. So our solution, finally, to this last problem here is 23, where x equals negative 1, once again, was an extraneous solution. All right, when we come back, our next section, we're going to talk about some more solving equations, but this time it's going to be equations a little bit more with factoring, using this thing which is called the square root property and the quadratic formula. Once again, all of that at this point should be reviewed, but good for us to go through.